right, welcome. You'll have to excuse my voice, and I appreciate you guys doing the video today. I'm pretty sure my son got a cold. I don't think it's COVID, but I'm pretty sure my son got a cold from school and brought it to me. So I'm gonna try to talk as little as possible through the day. So I'm gonna do this video so that both classes can watch it, and I only have to do this once then. So here we go. We're in 3.4. Which is on solving rational equations and radical equations. So let's begin. We're going to start with things that look like this. So we're asked to solve for x. We're essentially trying to figure out when this function on the left is going to be equal to 0. So one of the nice, easy ways to get to do this is to get rid of the denominator altogether. So my lowest common denominator here is going to be 6, right? It's a 3 here, a 2 there. The lowest common denominator is the number, the smallest number that is divisible by all of the denominators in the problem, and that is 6 in this case. So if I don't know what just happened. If I just gonna take this and move it a wee bit over, I'm gonna multiply both of these fractions by 6. Just 6 or 6 over 1. The reason I can do that is because I'm using the multiplication principle of equalities, which says if you multiply both sides of the equation by 6 or by the same number, then you still have that equality. And so the 6 will cancel out here with the 3, but leave a 2. So that's a 2 that gets multiplied by this x minus 8, which I'll just distribute through as 2x minus 16. The 6 cancels with this 2, leaving a 3 that gets distributed through the x minus 3. So I'll distribute that. That gives me plus 3x and minus 9. And then on the right-hand side, 0 times 6 is still 0, right? And just like that, I don't have I don't have fractions anymore, right? They're gone. So I can combine like terms. My 2x and my 3x will give me 5x. And then minus 16 and minus 9 is minus 25. And that's equal to 0. Right? So then I just add 25 to both sides. That leaves me with 5x equals 25. Divide each side by 5, and we're done. And that's it. That's the solutions to this problem. Right? All right. Let's look at this one here. I have x squared over x minus 3 equals 9 over x minus 3. So in the previous problem, we had these denominators that I wanted to clear, right? Let's just swing back up here. We had these denominators. One was a 3, the other was a 2. We came up with the lowest common denominator of 6. In this problem, this next problem that we have here, both of our denominators are the same. So my lowest common denominator is that. simply x minus 3. Okay. Which means that I can multiply both sides of the equation by x minus 3 to clear the denominator, right? Now, there's something that we have to be careful with, and we'll come back to it. Right? But we're getting rid of that x minus 3 out of the denominator here, right? And so on the left-hand side, this x squared, if I distribute it through, I get x to the third minus 3x equals, on the right-hand side, oh, I'm sorry, my bad. We're going to blame it on me not feeling well. Yoink. We don't want to distribute. What we want to do, since we've multiplied both sides by x minus 3, x minus 3 just cancels the x minus 3. That x minus 3 cancels that x minus 3. So I've got x squared equals 9, right? And so you can solve this in a number of ways. You can square root both sides. Square root of x squared just gives you x. Over here, though, we have the positive or negative root of 9. So that is plus or minus 3. So right here, it looks like we have two solutions. X is negative 3 and x is positive 3. Let's take a minute and throw this back into the original equation to see if they actually do. So I'm going to try negative 3 first. And if I plug negative 3 into the equation, this gives me, let me get rid of, oops, that and that. I'm going to check negative 3. So negative 3 squared over negative 3 minus 3 should equal 9 over negative 3 minus 3. Plus, you can see that this is going to be true. Negative 3 squared is 9. Negative 3 minus 3 is negative 6. This should be equal to 9 over negative 6. And obviously it is. They're the same fraction. So we can call this one good. Right? The issue is when I check x equals 3. So that would be 3 squared over 3 minus 3 is equal to 9 over 3 minus 3. The 3 squared is 9, but this 3 minus 3 is 0. And while you can say, well, it's the same fraction, they just happen to be over zeros, but whenever we get a 0, this is not in the domain. And therefore, we remove 3 as a possible solution. So we only have one solution here, and that is x equals negative 3. So that's what we are to be careful with up here, is when I multiply both sides to eliminate x minus 3 out of that denominator, it doesn't eliminate the fact that that denominator was there to start with. And so we have domain issues that we have to watch out for. So be careful with those. Watch out for those. When you clear your fractions, make sure that you understand that the domain issues that were in the original problem carry through the entire problem. All right, let's look at something bigger. Let's take 2 over 3x plus 6 plus 1 over x squared minus 4 equals 4 over x minus 2. So again, if I want to clear my denominator, I need to find the lowest common denominator in order to multiply it through, right? So that probably means that I want to factor my denominators, because I can figure out what the lowest common denominator is if I know what the factors that make up these guys are. So this first one, both the 3x and the 6 are divisible by 3, so I'm just going to factor out a 3. That leaves me x plus 2. The other one, this x squared minus 4, is the difference of two squares, so you'll recognize that as x plus 2 times x minus 2. And then this last one is just x minus 2. There's nothing to factor. So I have x minus 2 that appears. I have x plus 2 that appears. And then I have a 3, right? And that's my lowest common denominator, is the product of each of those three factors. So my lowest common denominator needs a 3. It needs an x plus 2. And it needs an x minus 2. Right? So that's what I'm going to do with all of these, is multiply by that. So this, I'm going to write this as in this way, x plus 2. And I'm just going to give myself a humongous amount of space, just to, you don't always have to do this, but when I'm teaching, it makes it look a little bit less hectic. I'm going to multiply by 3 and x plus 2 and x minus 2. And I'll just multiply everything. That way I'm using the multiplication principle of equalities. All right, so there's a lot there, but things that'll cancel out. This 3 cancels out with a 3. The x plus 2 cancels out with an x plus 2. And the next one over, an x plus 2 cancels with x plus 2. X minus 2 cancels with an x minus 2. And x minus 2 cancels with an x minus 2. Right? So if I clean it up a little bit, I have this 2. I'll just distribute through the x and the minus 2. So that's 2x minus 4. This is just 1 multiplied by what's left, which is 3. So plus 3 equals, then over here, I've got 4 times 3, which is 12. And I'll distribute that through x plus 2. And I have no more denominators, right? But it is, again, important to note that my domain issues here, x can't be 2 and it can't be negative 2. No matter what happens, I still can't allow those. They're not solutions, right? I don't know if I can fill this box in enough to make sure that you understand, once there's a domain issue, there's always a domain issue, right? That help? All right. So then we just solve this, right? So on the right-hand side, I can simplify negative 4 and 3. This gives me 2x minus 1 equals 12x plus 24. And then minus 2x, I'm going to get the 2x's off to the right-hand side. So I'm going to subtract 24. That gives me negative 25 equals 10x. And then if I divide each side by 2, I need to scoot this up a little bit here. Not by 2, by 10. Then I get negative either 2.5, or if you want, negative 5/2, but that's my value of x. This, when I check against the domain issues, is not one of them. So that's it. That's my answer, and I'm good with it. So those are our rational equations. And kind of similar to those are radical equations. So those are things that look like maybe this. Or sometimes you just have, right? So we're going to start with this one on the right because it's easier to deal with. And then we'll look at what happens when you have this kind of ugly thing on the left, right? So if I have, let's do this one on the left, or on the right, sorry. If I have it, just write it again. So the square root of something equals 4. All I really need to do to eliminate that square root is to say square it, right? But again, we have to be careful because this square root has some domain issues. That domain says that 3x plus 2 has to be greater than or equal to 0. Otherwise, I'm trying to take the square root of a negative number, which will give you something not real, right? So if I solve this to figure out that domain issue, divide each side by 3, and there it is. So I've got x has to be greater than or equal to negative 2/3, right? This is the domain of the original problem that we started with. Therefore, no matter what I do to this thing, it's never going to get rid of that domain issue. It's always going to be there. When I square both sides, this turns into 3x plus 2 equals 4 squared, which is 16, right? Now it's easy to say, oh, there's no domain issue in this thing. But it does, and that's true. There's not in this equation, but this equation is only valid on the domain of the original problem, right? So only valid on the domain of the original problem. Right? So we would say this is a representation of the original equation limited to x being greater than or equal to negative 2/3. And then we can solve this. Subtract 2. We got 3x equals 14. Divide each side by 3. And I've got x equals 14 over 3. And I'll just want to check to make sure, is this in the domain? And it is, because it's greater than or equal to negative 2/3. Right? So we're good. So that one's not terrible. Let me get out of here real quick. It's not, excuse me. All right, excuse me, sorry. Okay. My notes here disappeared. There we go. Okay. All right. There we go. Okay. So what if I have something that looks like this? question is, can I just come in here and square that and square that and square that and call it good? The answer is no, you can't, right? For example, to see why you can't, there's an equation. And if I just start squaring everything, right? First off, that equation was true. 2 plus 3 equals 5, right? But if I square everything, that gives me 4 plus 9 is 25. That's not true, right? Nope, no. So you can't square individual terms. What do you have to do? Okay, that's gone. Boink, it's back. What you have to do instead is square the entire side, right? So I can't square term-wise. What I can do is square the entire side. So then the next question is, do I want to do this? Square that 5 plus root x plus 7, and then square the x squared. And I'll submit to you that I don't want to do that, because to square this 5 plus root x plus 7, that means I'm taking 5 plus the square root of x plus 7, and multiplying it by itself. And you're going to work this out, and you're going to get a huge expression that's ugly, but still has square roots in it. This x plus 7 is going to still pop up in there. And if you actually do this, you're going to get 10 root x plus 7 plus x plus 7 plus 25. Right? So that's ugly. And it doesn't solve our problem. We still have a square root hanging out there. So that's not going to work. It's not also take freaking forever. So what do? Well, the one thing I can do is get rid of this 5 straight out of the gate and just say, you need to go away. And by doing that, I isolate this square root. So that when I come in and say, oh, great, if I square both sides now, the square just kills the square root, and that leaves me with x plus 7. And this is probably the easiest way to go about this, because now you have no more square root. Over here, you have an x minus 5 that gets multiplied by itself. So I have x minus 5 times x minus 5. The result of this is going to be x squared minus 10x and then plus 25. That's not too bad. I can live with that. In fact, I can subtract x from both sides. And because it's a second degree polynomial, I'm just going to take everything to the one side. So I'll also subtract 7. All right. Leaving you with 0 on the left. X squared minus 11x plus 18. And then we just want to factor this thing. Right? So if I factor x squared minus 11x plus 18, if I look at the factor pairs of 18, we got 1 and 18, 2 and 9, and that's as far as I need to go, because if I let these both be negatives, that gives me my negative 11. So I get 0 equals x minus 2 and x minus 9. Right? Again, if this product of these two things equals 0, then either x minus 2 was 0, or x minus 9 was equal to 0. And so if I add 2, I get x equals 2. If I add 9, I get x equals 9. So it looks like I have 2 possible values, right? But if I go back up to the equation, the original equation has this x plus 7 under a square root. That might be an issue, right? So with the square root of x plus 7, that's not helpful. With the square root of x plus 7, this tells me that x plus 7 has to be greater than or equal to 0. anything outside of that is not in the domain. So if I subtract 7, well, then I've got x has to be greater than or equal to -7, right? And both of these are greater than -7, right? Something tells me oops. Oh, right. Sorry. So they're both within the domain, but the one thing that we now are needing to be careful with is that this original equation here with the square roots doesn't necessarily have two solutions, right? When we square something, so at this point right here, we've introduced a new equation that's equivalent to that for the most part, but this has two solutions because it's a second degree polynomial. This one only has one, right? So we still need to check our answers, even though they're both within the domain. I still need to check to see if they both work. So I'll check into the original, which was 5 plus the square root of x plus 7 is equal to x, right? So if I check, say, 2, let's check 9 first. If I check 9, that's 5 plus the square root of 9 plus 7 is equal to 9, right? Well, that's 5 plus the square root of 16 is equal to 9. The square root of 16 is 4. So I have 5 plus 4 equals 9, which is true. That one checks out, right? But what about 2? Let's check it. That would mean that 5 plus the square root of 2 plus 7 is equal to 2. But that is 5 plus 2 plus 7 is 9. And so I have 5 plus, but the square root of 9 is 3. And it's not true, right? And you can see possibly why this would end up having two solutions if you work this backwards from where we took our square. If you had this equation right here and square rooted it, you would end up with a plus or minus in front of this the square root, but we don't have that to start. Therefore, when we square it, we ignore the fact that there was positive and negative potential from the equation that we're creating. And so it introduces a false solution, which you can typically see by if this were a negative right there, then it would have been true, right? So that's kind of why we see those. But whenever you have a square root equation, there's always the potential that you're going to introduce solutions that are not real or that do not actually exist. So check. All right, so let's take a look at, let's do one more of those, I think, before we do the next kind. Let's look at square root of 7 minus x equals 2 plus x. Actually, I'm not going to make one up because that might not work out very well. I'm going to do 7 plus x equals x plus 1. We don't want to deal with something ugly right off the bat. So, but again, I'm going to, this is already isolated, so I don't have to worry about that. So I'll square both sides. Squaring the root just turns it into what's under it. But squaring 1 plus x is taking 1 plus x and multiplying it together. So that's going to give me 1 plus 2x plus x squared. If I subtract x from both sides and subtract 7 from both sides, then I have negative 6 plus x squared. Or if you don't like the way this looks, turn it around. Okay. But here I can factor this into x plus 3 and x minus 2. And then this would tell me that either x plus 3 is equal to 0, which tells me that x equals negative 3, or that x minus 2 equals 0, which tells me that x equals 2. Both of those are in the domain, so we're okay, but I do need to check. One of these will be valid and one of them won't, most likely. Check. Again, the original function was the square root of 7 plus x. Equals 1 plus x. So if I check negative 3, seven plus negative 3 or 7 minus 3 is equal to 1 plus negative 3. 7 minus 3 is 4. 1 minus 3 is negative 2. But the square root of 4, right? Because it's the square root sign, that means the principal. There's no plus or minus here. It's just 2. And so this one's not true. If I check 2, this gives me 7 plus 2 equals 1 plus 2. That's root 9. The right-hand side is 3, and that one is true. So then the answer is just that. It's x equals 2. That's the only one. All right. Let's try the little bit uglier one. When you see a problem that looks like this, it gets a little bit hairier. Because there's 2 square roots here, right? And on that first one that we did with a square root, I said, oh, you don't want to square root something where there's a square root. You don't want to square something where there's a square root plus or minus something else. Well, here we have no choice, right? So what I'm going to do is I'm going to subtract the square root of x plus 5 on both sides. And that gives me the square root of x minus 3 equals 4 minus the square root of x plus 5. Okay. Now, if I square both sides, I'm going to do so because doing that will get rid of this square root on the left. But on the right, I have no choice. I just have to go down that ugly path, right? So this frees up the x minus 3. But over here, this is that 4 minus the square root of x plus 5 times 4 minus the square root of x plus 5. There's no way around it, right? And I'm going to FOIL. So you have 4 times 4 is 16. 4 times this negative square root just gives me negative 4 root x plus 5. And then the minus root gets multiplied by the 4, so I get another minus 4 root x plus 5. And then the minus and the minus cancel out to give me a plus. But the root x plus 5, the root x plus 5, that's like squaring it, so that just gives me x plus 5. Okay. So I can clean it up just a little bit. On the left, I had this x minus 3. On the right, I've got x. I've got plus 5 and plus 16. And then I have these two terms that are the same, the root. So I get minus 8 root x plus 5. So what did that get us? Well, now I only have one root. But guess what I have to do? I have to get everything away from that root, shove it off to the other side, and square again, right? So I will. I'll subtract x from both sides. That's gone. That's gone. 21. I'm going to subtract the 21 to the other side. So that's gone. So we get negative 24 equals negative 8 root x plus 5. And I can divide both sides by negative 8 because they're both divisible by negative 8. Make life a little bit easier here. Negative 8 and negative 8 cancel out. So on the right-hand side, I just have that root of x plus 5. And on the left, the negatives cancel out. But 24 divided by 8 is 3. So this one's not too bad. I can come back in, square this, square that. On the left, I get 9. On the right, I get x plus 5. And if I subtract 4 from both sides, I don't know why I would do that. Let's try that again. Oops. I want to subtract 5 from both sides to get 4, and I'm done, right? But whenever you square something to find a solution, you want to check this. So let's check it. X equals 4 into the original equation, which was x minus 3 plus root x plus 5 equals 4. Let's check it. If it works, then 4 minus 3 under a root plus 4 plus 5 under a root should equal 4. 4 minus 3 is 1. 4 plus 5 is 9. That should equal 4, and it does. That's 1, that's 3, and those things equal 4. So it's a solution. That solution was x equals 4. So those ones have the potential to get a little bit ugly. I'm going to do one more of those just because they do have the tendency to just uglify pretty quickly. Let me try. We'll try this one here. This is root 3x minus 5 plus root 2x plus 3 plus 1 equals 0. This one's not going to have a solution. I can see that already. So I don't want to waste my time on this one. Just going to double check in case I'm wrong. I don't think I am. Yeah, that one doesn't. Let's do this one. The reason that I can see that right from the get-go, if you're interested, is if I'm just going to do it quick here. If I subtract 1 to the other side, this is the positive square root of something. That's the positive square root of something, and now it's equal to a negative number. So it doesn't work. This will have no solutions. If you worked this one through, you would end up with 2 solutions, and then neither of them would end up working. So, but yeah, that's dumb, and that was a waste. Let me work this one, which will have valid solutions. 2m minus 3 is equal to the square root of m plus 7 minus 2. This one will have a solution, so let's try it. Right? I'm going to square both sides. So square that and square that. That gives me 2m minus 3 on the right, or on the left-hand side. But over here, remember, this is a binomial, so squaring it means taking that m plus the root m plus 7 minus 2 and multiplying it by root m plus 7 minus 2. The roots multiply, that gives you just m plus 7. And then minus 2 root m plus 7. And then minus 2 root m plus 7 again. And then plus 4. So I'll clean it up a bit here. I've got 2m minus 3 equals m plus 11 minus 4 root m plus 7. If I move the m to the left and the 11 to the left, and I get m minus 14 equals negative 4 root m plus 7. Right. Now this is where it gets a little bit ugly, because I still have to square to get this out of here, right? And so if I square the left-hand side, that will be m squared minus 28m plus 14 squared is 196. On the right-hand side, though, then I've got, when the negative gets squared, it goes positive. So that's 16, but it's multiplied by the square. So it's like taking negative 4 root m plus 7 and multiplying it by itself, negative 4 root m plus 7. But this is all just product, so I can just write this as like negative 4 times the root of m plus 7 multiplied by negative 4 multiplied by the root of m plus 7. Multiplication's commutative, so I can say this is like negative 4 times negative 4 times root m plus 7 times another root m plus 7, right? Doesn't really matter how you think of this. Negative 4 and negative 4 multiplied gives you that positive 16, and then the root of m plus 7 multiplied by the root of m plus 7 gives you m plus 7. Well, that 16 has to get multiplied by all of that. Excuse me. So m squared minus 28m plus 196 is equal to 16m plus 70 plus 42. Just check that because I don't trust anything right now. That's right. And so I'll get everything to the left. So I'll subtract 16m and subtract 112. Some pretty big numbers here. But this gives me m squared minus 44 m plus 84 equals 0. And then I can see if I can factor this. 84, 1 and 84, that's not it, but 2 and 42. If they're both negative, will give me what I need. So this is m minus 2 times m minus 42 equals 0. And so m equals either 2 or positive 42. And again, I need to check. So I'm going to take the original just make sure that's right for a second here. Where was it? 2m minus 3. Yeah. Okay. Yeah, I'm going to check that. All right. I'm going to check 2. 2 is the easy one, so I'll plug that in. That would be square root of 2 times 2 minus 3 equals the square root of 2 plus 7 minus 2. This is 4 minus 3 under a square root, which is just the square root of 1, which is just 1. Over here, this is the square root of 9 minus 2, which is the square, which is just 3. Minus 2, and that's 1. So m equals 2 is a solution, which means it's pretty likely that m equals 42 is not. It's a good thing they have such small numbers because this is going to be cool. 2 times 42 minus 3 should equal 42 plus 7 minus 2. This would be 84 minus 3 should then equal 49 minus 2. 84 minus 3 is 81. Square root of 81 is 9. Square root of 49 is 7, but 7 minus 2 is 5. And so 42 is not a solution. All right. Thanks for bearing with me. I apologize for the voice. Hopefully by next time it's not so bad, but email me if you have questions or concerns. We could throw solutions in the discussion on Canvas if you want to see things worked out or whatnot. But thank you. Have a good day, and we'll see you next time.